So AI for Search is the product of my company, 904 Labs, and it's a software as a service search suite for e-commerce that learns from site visitors' search behavior. What does it mean? It means that we're applying state-of-the-art search technology on product search in order to make on-site search better for our customers. 904 Labs was founded in 2014 by me and my co-founder and also ex-colleague Wouter Verikamp. And we founded 904 Labs because we were in academia for about 10 years. And after finishing our postdoc, we were thinking what we want to do next. And we had offers, and we could go and work for big companies like the Googles. And but we decided, or to continue to academia. But we wanted something new challenge. How can we bring what we do into the market, like try to make an impact? And we thought, well, you know what? We have all these algorithms sitting there, getting dust, but also the research community that we know very well of, they do great stuff, great algorithms, but they're not really being used in industry, or they're used by the very few ones. Why not make all these great algorithms accessible to the market? So I said, okay, let's do it. That's fun. So let's democratize search. That was our motto back then. And we joined ACE Venture Lab Incubator, which is an incubator supported by the University of Amsterdam. And through the mentoring program, which lasts about 1 or 2 years, they also had a bootcamp program, an accelerator program. But let's say that we stayed there for a couple of years. We learned a lot on how to make business models and business plans, and pitch a lot to everyone and their family. And it was very exciting times. At the same time, University of Amsterdam itself ran some sort of a funding branch from which they support startups that they are data science driven. So we were part of this profile, and we managed to get 2 proof of concept loan and a pre-seed loan with very good terms, and that's how we got started. Right now, we are serving traffic from 4 countries, and and there are about 12 countries in the pipeline, and we add 1 country every week. Things are looking good, looking pretty good. We're a very small team. We're about 3 people. Depends, 4 people, depends how you count. We have an ambassador in the US, which is great, for doing business development there. But the cool thing is that we are a very, very small team, and we are serving traffic that is quite large. And infrastructure-wise, we're doing very well. Scalability-wise, we're doing very well. And I think this is some sort of a lesson that I would like to communicate to you, that if you do a data science startup and you build a data science product, you can actually afford a very lean start. Because if your algorithms perform well and they're optimized, then you don't need to have 100 people personnel to fine-tune things. Having said that, we found that research and markets have been further apart than we first thought. We thought that we would go to the market and everyone would, embrace us and say, "Oh, God, guys, of course, oh, you have this great research algorithm? Of course, bring it on. We'll remove our CMS that we have for 10 years because, you're going to increase our revenue." And they did understand that we were going to do that, but the implications, the engineering and business implications were so big that some of the customers would say, "I'm sorry, we really want to, but it will take 2 or 3 years until we can put your system for the integration pipeline." That is one thing. So money started running out, and then we started to look for funding. And what we our experience with funding in Amsterdam was that the investors that we talked to, they wanted to have lots of proof that the product works, which is kind of, I feel, against of investing into a startup. And I mean, if you go to a bank, then the bank will ask you, okay, yeah, sure, am I going to get my money back? It's a bank, it's all right. But if you're talking about a business angel or an investor who's interested in investing in startups and they ask all sorts of guarantees, then it becomes a bit tricky. So we've never, we came close, and then we decided that we don't want to do this, and we didn't pursue any funding. The final bits, lesson learned that I have to share with you is that if you're a team of friends that are really great in engineering and you're going to make a startup for a product, please find another friend who's very good in business, and vice versa. To have a team with complementary skills, it's paramount importance. I'm a geek myself, and my co-founder is a geek himself. We're very good at sitting and thinking about code and writing codes, but when it comes to go and sell and push for a sell, that's not our hardest, our best skill, and we did need that. So complementary skills in a team. I think these are the three main points about building a startup in the Netherlands. All right, now let's talk about search, finally. That is my favorite topic. I don't want to just dive into the algorithms, because I think I'm going to miss a lot of you through the process. So what I want to do is to first move from this real world slowly into the search world. And how I'm going to do that is to first bring some examples on why search matters and how search is easy to miss, and then dive a little bit deeper into how search works and how machine learning helps search to work. And then I'm going to get back again with some examples, and then we'll exit. Okay, let's do it because we don't have enough time. So usually search is when I talk about search right now, I'm referring to e-commerce sites and on-site search. So think of Amazon.com and the search bar that they have there, and someone enters and they start searching, and then you get results. Most of the e-commerce sites, because they have a search box, they think that search is fixed, is solved. However, when other departments in the same company run some other campaigns, sometimes these campaigns are not aligned with search. And I'm going to give you a couple of examples. So here is Thuisbezorgd.nl, which is a delivery or takeaway website, and they have put an advertisement on the streets, and they ask me whether I would like to have Indian food. And of course I do, because I like it very much. And okay, it is on my way back from work. I don't stop at the supermarket, I just go straight home, and then I go on the website and I type Indian food here in the search box, and then there's only one restaurant popping up. Okay, that they must have paid a lot of money to have an entire marketing campaign throughout the city for this one restaurant. Something else must be wrong. So I abandon the search box, and I go to the filters, and then I through the categories, I find the Indian food category, and then I see that there are at least 4 restaurants in Amsterdam that can do that. So that is a bit better. Why my search fails? Because they chose to search only on the title or on the name of the restaurant. Although they do have the category information, they chose to ignore it. So that is one example. Okay, you may say, right, it's one website. Let's go somewhere else. So the other day, I received this catalog, this printed marketing catalog at home, and it was a nice Sunday morning. I was drinking my coffee, I opened it up. I see this beautiful fridge. I say, all right, this is exactly what I was looking for. I wanted to throw away my old one. I want this. Okay, bring it on. I open my laptop, search, inbouw cooler, which is the fridge, that instant fridge, I guess. No results, the website says. Huh? But it was on the catalog. I want it. They promised to me. Well, if I abandon search again, and then I go through the navigation of the filters, on the third page, I find it. And there are lots of fridges there. And the problem is that they advertise fridge with the word cooler in Dutch, but they have it as koelkast in their catalog. And their search system did not know the mapping between cooler and koelkast. So this is what happens when departments do not align well with search. And these are two examples, but believe me, there are many, many, many more like this. So search is overlooked, and but it is also more important when it comes to mobile devices. Because in mobile devices, you have smaller screens, so good ranking matters the most. So here's something that I did. I went on my phone and I searched for a particular mobile phone, which is Samsung Galaxy J5. On 4 major e-tailers in the Netherlands, that is bol.com, Coolblue, Conrad's, and MediaMarkt. There is very little space, as you see. In most of them, you have only one result. And in that result, it is very important to make it count. AKA, do not bring up a charger, do not bring up a lamp. Just bring up the phone. That's mobile. All right. I think I got your attention with that search. Sometimes we think it works, but actually it doesn't. The fact that it works on Google, it's not enough. There were a couple of slides there. They were gone because we don't have enough time. But search is not only these examples that I talked to, but they are in many other tasks. And some other tasks are, of course, well, your web search engine. We all know Google. It is called search. But also in recommendations. So if you go to Amazon or wherever else you get recommendations, it's exactly or similar type of algorithms. You have to figure out to rank a list of items in some order. So first you need to score the documents and then rank them. Same thing. Another application is Tinder, which is also a type of recommendation algorithm, but this time the recommendations are coming one at a time. That's the only difference between people who also bought that and Tinder. And about the latest addition of at our homes, the personal assistant. It's also the same. You give it an input and it gives you an output, which is your input is a search query and the output is the search results. So exactly the same search mechanism work there as well. Now, a little sidestep, and I think it is important about voice search. Voice search is booming, especially with our mobile phones and Siris and Cortanas. The difference between standard search and voice search is that voice search is longer because we talk to the machine and our queries become longer and they have more of the, little words, stop words like and then and to. And another thing is that because it is longer, it has more of a conversational flair. So for example, I will say, hey Siri, please show me some blue jeans I want to buy. And then Siri will return me blue jeans. If I say, oh no, I don't want blue ones, I want red ones, Siri should not search red ones, but it should search red jeans. So it is about NLP and also understanding which parts of the query and going back to the conversation and keeping context. Now, these are the main differences, and they are important because voice search, as I said, is booming. This picture is from 2 years ago from Google, and this is the volume of their of their queries, of their voice queries. The graph goes from 2012 to 2014 or 16, and the peak is a few billion queries. It's insane. All right, now that we have an idea of search, how search works. It is very simple. You have a collection of documents. Think of A4 papers full of text, and then you tokenize the text as in you take only words, you put them in an index so you can keep some statistics of each of these words. And then when someone queries the search engine, so for example for blue jeans, you go into your index and you say, all right, give me all the documents that have the word blue in them, and you do that, and all the documents that have the gene. And then you combine all these together, and then you need to figure out a score, how to score them in order to rank them and get the result list that you have on the right. So the main goal of search is how to match and rank documents that are relevant to the query. The word relevance is crucial and has troubled the research community for at least 50 years. Now we're moving away from the word relevance and we're talking about utility, which makes more sense, but that's a very different topic. This is a little bit of a history of search. It started in 1950, it was Boolean search. Documents were ranked whether they included one of the query terms or not. And then it took us about 20 years to discover document frequency, which is how important is a term within the collection. The importance of a term is if a term like the occurs in all documents in the collection, then it is everywhere and therefore it's not that important. But if you have a term that occurs, for example, in 10 documents out of 1,000, then that term might be important for those. Or at least this is the theory behind document frequency. And then 20 years later, we arrived at BM25, which is the algorithm that is currently state of the art. If you go to Elasticsearch or Apache Solr, if you know these systems, this is what they currently use. This is from 1990. Then in 2000, PageRank was discovered. And Google happened. However, we cannot really use PageRank for e-commerce. We do need links. We do need a graph structure in our data. And then only the last few years we have learning to rank and machine learning or AI for search. But you may think, all right, search is important and has a long history, but what do we really need AI for search to do all these kind of things? Well, let me give you an example. This is the only formula in the presentation. This is the term frequency. This is how we use to compute the ranking of a document, the score of a document. Let's take the term frequency, which is how many times each of the query terms occurs in the document, times the IDF, which is the inverse document frequency of the query term in the collection, which means how many times have we seen, how many documents out of which do have this term. If we multiply these two, we get a score. This is the TF-IDF score, and that has been the standard scoring a couple of versions ago before Solr and Elasticsearch. All right, that's pretty easy. I don't think we need search, you may think. Sure, but enter the e-commerce world. They said, well, sure, but you know, we have now multiple fields in our document. We have the title, and but we also have the query, and we also have the synonyms. All right, the synonyms. So we do not have the problem with coolcast and cooler. All right, let's do TF-IDF of the coolcast as well. All right, 2. And now we have the title and we also have the description. All right, then let's search there as well. Okay, then we have 4 items to search for. And we also have 4 different ways of weighing the effects of each one of these factors. Are you following? 4. All right. So far, so good. But then again, what about popularity? Shouldn't more popular items be at the top? I search for Harry Potter and I click on the Blu-ray edition, not the book. It's more popular, so it should go up. Okay, all right. Yeah, but the DVD edition is actually making us more money. So let's put margin, profit margin in there as well, and then we have the score. All right? Okay. But if an item is new, we do not have popularity information, and that will zero out our score. So we will assign a arbitrary score to new items to account for that. And if the item is running out of stock, then we're going to low down the ranking because we want to push other documents to the top. And that it doesn't stop there. It goes a long way. You cannot imagine in what extent of creativity people have gone into designing this kind of search functions. Nevertheless, we need to think that there are lots of weights and factors that need to be counted in. The message here that I want to bring to you is that search is too complicated to solve manually. That's the problem, and that's why we need machines. Especially if we want to go beyond and over more complicated scenarios where we want to track our marketing advertisements and what is on the streets and which products are in booklets. What is the weather outside? If it is warm, I know, and we have seen that in our data, that parasols, sun umbrellas become very, very popular. And now Easter is coming up. We do see queries about Easter. How are we going to count this in all? Let's leave the machines to do the learning and the ranking. So we have a bunch of features. So each document is represented as a bunch of features, like the date that it was added, the title, the description, the ratings, synonyms, availability, location, etc. Then we will assign a weight to each one of them, and then we will allow the system or ask the system to find the perfect way for them after it operates on these features. And then we'll get a score instead of doing that manually. The machine learning for search, or learning to rank, as it is called in academic terms, is try to find the weights that are optimal in order to optimize an objective function, which is a particular type of signal. And that signal can be clicks, it can be click-through rate, it can be purchase, it can be profit margin, it can be all of it. It doesn't matter, we just set it, and then the machine learns the rest. Yeah, that was a strange slide, wasn't it? All right. This doesn't mean, so this is what we do, what I described. What we do not do is what I show here. And this is some that some of the companies and competitors that we know of claim that they do AI for search, but this is what they do. I'll explain to you straight away. A query comes in, and then people click on the documents, and then we record how many times a document has been clicked for a certain query, and then we rank by the popularity. This is it. Is there data science in there? Well, there is the fact that we're keeping track of the clicks per document, but it doesn't solve the major problem that we don't know how to rank documents for queries that we have not seen, and we don't know how to rank documents that we have not seen either. So it is not what we do. It is what we do is this. We get a query, as I said, we have these features, then we get a ranking of documents, and based on clicks, we change the weights of these features. This is how it looks like. On the x-axis is a bunch of features that we have in our system, and then this is at a very initial stage. We have trained, the system has been trained on 44 out of about 2,000 queries with clicks. And then at second points, then we do see at 300 points to have the weights to have increased, and a bit later some others. And finally, we have a different distribution of weights from those that we have started from. And we can also rank them, and then we can see that some features are more important than others. For example, those that are on the upper side are positive and have positive high weight, and those that are on the lower side are less important. There are two ways to do learning to rank. One is batch, and one is online. I don't have enough time for this, I'm afraid. I'm going to focus only on online learning to rank. This is what we do. If you have used scikit-learn, scikit-learn is doing batch learning to rank. The difference is that with online learning to rank, you can learn online with every click, and it is based on reinforcement learning. So the model starts at a certain state, it exhibits the ranking to the user interacts with the ranking, and the model updates its states to the next one for the next user. In order to build a system like that, you need to have three items. One is exploration, so you need to explore how you're going to rank, to explore your weight space. You also need to have feedback to inform the system if it did a good job or a bad job, and you need to have an online algorithm. That means that it should adapt with every click. For example, if you think of a neural network with more than 3 layers, then it will take a lot of clicks before we'll see any differences in the weights. This is how it looks like, the exploration phase. Let's think that we can use Google as an example, and we have searched for search engines that learn from their users, and then we get these 4 documents, and let's say that we have a system, Google A, that has a certain type of weights that has learned, and another version of Google B with a different type of weights. In order to figure out which of the 2 weights are best, then we interleave the lists, as in we take the first example from the blue list, followed by the links of the red list, and then we check where the user clicks. And whether the user clicks, then that means that the red or blue is the winner, the one that receives the click, and then we can make a decision on which set of weights is better. Now, if we start perturbing with every impression the weights by a slight margin, then we can perpetually create this A and B, but A and B will always be the winner of the previous time, and B will be a perturbed variant of it. And this is how interleaving or dual gradient bandit descent works in order to find an optimum through the search space. The feedback can be clicks, which is abundant. It is noisy, but we do know that it does a great job. But there are other signals that we can take into account, like add to baskets, email, favoriting, or whatever the UI allows us for. Now, how all these look like when we put them into a real system? This is how it looks like. On the left-hand side, you have the results of pilots we did with Vita Excel on their Dutch website. And when you search for koffer, which means case in Dutch, you would get lots of cases, toolbox cases usually, and phone cases. And only lower down, you'll start seeing traveling cases, suitcases. When we trained our system based on user behavior, our system popped up travel suitcases with a nice assortment between those that are on sale, and there are a bunch towards the end that are neither on sale or new, and some of them that are new. Another example on the final one is the word kitchen, where the manually ranking Solar, it has toy kitchens at the top. And there's also a fruit scaler there, I guess. And in our system, from after following user behavior, we do see kitchen cupboards. And these are kind of differences. We've measured them, and they added about 26% on Vida's revenue. It was quite insane. Now, what happens when you train different models between different countries? This is when we search for Vida Excel on the Netherlands. On the Dutch side, it is dominated by party tents. This is how they're called. I guess in the Netherlands we like to party in the garden. But if you search for the same thing in the French websites, then it is a bit of a more random assortment with a type of preference towards chairs. And if you do the same in the German websites, then we do see mostly tables, and there's a nice fitness cycle on the top. The take-home message here is that different countries or different user groups, they have different dynamics and user behavior, and they may require different results in order to persuade them to make a purchase or to revisit your website. There are more into it. I do not have time for it. It is about learning synonyms automatically, straight from data. Here I have a list of examples. The most prominent one is that the system has learned that Karcher is a synonym for vacuum cleaner. And that brings me to my conclusions. Search powers many aspects of e-commerce. It is easy to oversee, but it is very important. It powers many applications, recommendations, and conversational search and chatbots. It is very complicated for humans to solve because the search space is humongous, and therefore we do need AI in the end in order to tackle this problem. And when we do manage to have this AI model trained and looking into the finer grains of search, then we have shown that we can boost revenue or other KPIs for customers. And that is it. Thank you very much.